Okay, quick little sound check here. Sound is fantastic. Okay, so welcome back to another exciting Atari 5200 programming stream. So today, we're going to pick up where we left off from last week, mostly. So last week I started putting together a demo of Antic Mode 4, which is very commonly used in games. Now, it is a character mode, technically, like Mode 2, which you covered before, which was used for text. But the difference is that it allows for multicolored character tiles. So people often abuse it as a tile engine for games, which is what we're doing here. And I've decided to just do a simple Tetris game for a couple of different reasons. One, it's simple. Two, it's an excellent demonstration of Mode 4, because it is in itself a tile-based game. So it demonstrates Mode 4 very well. And lastly, I have some plans for a game of this type in the future that I'm going to do for the 5200. So I wanted to do a little bit of experimenting here, just to play around with some ideas and see how viable some of my ideas are. And so this is a little bit self-serving, but you know what? I don't care. So what we did last week is we got kind of a basic board set up, as you can see here. So I created, in effect, 3 different tiles that are in our character set, our custom character set that we're using here. The first is the blank tile, which is tile number 0, which is the one in the middle that we're using to blank out the board. The second tile is the little kind of hashed tile that's making up the background here, which is that's tile number 1, I believe. That's just like a staggered pixel on, pixel off. And the third tile we made is the one that's making up this nice little Tetris block that you see at the top of the pit here. That is tile number 2. So where we left off last week was after I had written the routine to generate each of the 7 pieces at random. And we tested it out, and it places the pieces here at the top of the pit. And here I just started up the emulator to demonstrate what's going on. You can see there's the reverse L piece there. It was the one that just happened to get picked by random and thrown up there. Now, I did go and do a little bit extra. Earlier today, I wanted to do something. So I did alter one of the things that we wrote last week. And that was, we had written a subroutine that takes cell coordinates and converts them to the memory address of that specific cell. Because if we're going to mess with the graphics in the pit here, we need to know which memory address each cell is at. And we're going to need to use that a lot. Now, the original routine that we wrote last week was kind of a brute force thing that was very slow. It worked, but it was very slow. So I went ahead and redid it to a much, much faster algorithm. So what I did was I created a pair of lookup tables. As you can see here in the bottom half of the text, I'll highlight them here. So these 2 tables, I have row address low and row address high. These 2 tables encode the leftmost byte of each row of the board. So now the way that we look up the address is we take the row number, use it to look up the base address out of here, and add the column number to it. And that'll get us to the specific cell in memory that represents each space on the board. And you can see the routine here. This is the new routine. It's much smaller and much faster than what we had before. So the coordinates come in, just because it's the way I did it. The Y coordinate comes in the accumulator, and the X coordinate comes in X. So we put the Y coordinate in Y because we need it to index, and we put the X one back in A because we're going to add it to this. So we take the X coordinate and add it to the low byte of the base address, which we look up using Y. And then store that to FE, and then we add 0 to the high byte, which propagates the carry bit, if necessary, and store that in FF. So this is a very much smaller and faster lookup algorithm than what we had before. In particular, the algorithm we had before would have gotten progressively slower as you went down the pit. This one is constant time. It's faster and it's constant. So this is great. And I can see a track mode has just kicked in on the screen. So you know what? I should probably, while I'm thinking about it, I think I left The V blank. Yeah, here it is. We'll reset a track mode. Just for fun. Why not? Yeah. Should probably do that. Okay, so where are we? What are we doing here? So at the moment, all this thing does is when the program starts up and it calls this subroutine here called generate new piece. This selects a random piece and places it top of the screen. Last time I ran, we got that reverse L piece. We'll run it again, see what we get this time. Got the other L piece. So these pieces are being drawn, just in case you weren't here for the last week. Shame on you if you weren't. These pieces are being drawn from a table right here. Piece table. Right here. So what these are XY coordinate pairs for the 4 blocks that make up each piece. So see here we got the L piece. That happens to be the first one, piece L. So the blocks are at X coordinate 4, Y coordinate 0. 0 is the top row of it. These are 0-based indices. So 0 is the top row, 0 is the left column. So we're at X4, Y0. And it might be hard to pick out the individual squares, but that's where the first block is. And then X4, Y1, it would be 1 down. And then X4, Y2 would be the next one down. And then X5, Y2 would go over for the little hook on the L. So this table is what we're using to define the pieces when they enter the board. Now, the first thing I want to do today is to just get the pieces to fall down. That's step one. And so we're going to put whatever we've got in place, whatever we need to get in place to do that. So let's go ahead and get started with that. I'm going to leave the emulator up just because why not? It's fun to look at. What do I have commented out here? Oh, colors. All right. So we're going to need some memory locations to store a bunch of data here. So what data do we need in order to make this piece just kind of start to fall down the pit? Well, first of all, we need to know where the individual squares are. So the way you want to think about these pieces is not as solid pieces, but as collections of 4 squares. So we're going to look at each square individually and move it down. Down, down, down. And if we move all 4 squares down, the whole piece will move down. So we need a way to track where the current squares are located. So here's what we're going to do. We're going to name something called current piece X. And we'll set this equal to hex 19, which is the first available memory address on 0 page. And then we're going to have current piece Y, which is, we're going to put this 4 bytes after current piece X. That's going to be 1A, 1B, 1C, 1D. Okay. So the values at 19, 1A, 1B, and 1C are the X coordinates of our 4 individual blocks. And then at 1D, we're going to have 4 more values, which are going to be the Y coordinates of the 4 individual blocks. And this way we can track where these are. But before we can do that, we need to actually put those values in there. So we need to go back to the generate new piece routine and add a little more logic to not only put the piece onto the board here, but to also put the coordinates of the different blocks into our long-term storage so that we can maneuver them down the board. So let's look at this and see how we're doing this. So here we go. We're looping through the piece table. And we convert the values we get to an address. And this puts the address of the cell into FEFF. So we write a 2 to FE indexed by Y. Okay. Why are we indexing that by? Oh yeah, because you have to index by something to dereference an address. So we're indexing by 0. All right. So 2 is the character code for this tile that we're using for the pieces. That's why we're writing 2 there. But what we want to do, okay, this is actually going to be pretty easy, I think. Okay. So we need to write a total of 4 pieces. Here we go. Load X number 4. Okay, so we're keeping the looks like we were using FD as a counter for the loop. And starting at 4. But I think we're going to start this instead at 3, and we're going to change the logic around this. Where do we use FD? Here we go. Dec FD, branch and equal none. So we're going to change this to a branch on minus. See, now we can use that value in FD as a lookup index into our long-term piece storage. So what we're going to do then is, let's see. Thing is, we need to make sure this is going to be a little bit tricky because we got a lot going on here and we don't want to clobber anything. So we might have to do a little bit of register juggling here. So Y is the index into the cell table, but we clear it right here. So it looks like it's okay to clobber Y for the most part. Because we get it back from FC. Okay. All right, this is going to be a little slow, but I think it's okay. So here's what we're going to do. So the first value we pull out of the piece table is the x coordinate of the block. So we need to have this value. We need to put this into that location, but we need, it really doesn't matter what order we do them in. So here's what we're going to do. We're going to load Y. Okay, we loaded FC, loaded the first value. Then I'm going to, actually, I transfer it to X. Now, I don't think I can index a 0 page value with X, but let's see if I can. Wait a minute. No, never mind. That's not what I want. That was stupid. Never mind. So what we're going to do, after we load that piece, I'm going to, wait, I can just reload it. Okay, never mind. Okay. After we load that, I'm going to load Y with the value in FD. So this is an index that we can use to write to our long-term storage. So now I can write to current piece X, Y. And then before we look up again, we have to get the index back from FC. We load the next piece. And then we're going to, again, load Y, D, and write this to current piece Y. Now, I don't think Y is relevant for cell to address. I think it's just X. Yeah, we don't need to worry about Y. So at this point, we're good. All right, so a couple extra instructions, and that should record the piece data. So let's make sure it does. Go ahead and build it. Great. We're going to run it. Type the entire command. Okay, so we got the L piece again. Now, here's what we're going to do. We're going to break the emulator. Do a break. Now, we're going to look at the memory. And I've moved to a new emulator for doing these. It's a much better emulator than what I was using before, but I'm used to the debugger from the old one, so I'm still learning the commands in this one. And I don't know what the command is to display memory here, so I have to look at the help page. It looks like M. I think memory list is what we want here. Okay, so I want mem19. Okay, so here is the memory layout of what we currently have. And look what we got at that first address. Wait, why is it listing as 41FD? Maybe I don't put a $sign on it. It says to M19. Okay, there we go. So if we look here, starting at address 0019, which is the first one on the list, we see 0504, 0404, 0202, 010. That does not seem right to me. Oh, wait, hold on. It's all the X coordinates followed by all the Y coordinates. I was pairing them off. Okay, so we have... So the first block we wrote, then we actually started at the back because we started at index 3. So the first block we wrote went to 0400, which is correct. And then we have 0401, 0402, and then the final one is 0502. That is correct. So we now have the locations of the current set of blocks here stored in these 8 bytes of memory. using those, we can manipulate the blocks. So we'll go ahead and continue. I don't know what these commands. I'm just going to quit. I don't know what the commands are, so we'll just quit. But we're getting those. Those are being recorded now. So now we generate a piece. We get all the good stuff. Again, I'm having trouble typing. All right, so here's a square piece. Now that we have the coordinates of the 4 individual blocks recorded, what we can do is we can use those to drop the piece. So the next thing we need then is we need a timer. Okay, so we need to know when are we going to drop the piece. Now, in the long term, if you're doing a real full-blown Tetris game, which I don't think we're going to do here, you'd have to be able to change the value of this timer, because as the game goes on, you get to higher levels, the timer gets faster and faster. So in order to make the game faster, you would just change what value you write to this drop timer all the time. I think, at least initially, we're just always going to use the same value. We'll call it drop timer. Now, this is going to go... Okay, so remember, we have 4 bytes for current piece Y. So 1D, 1E, 1F, and 2-0 are all part of that. So we need to go to 2-1. And this is where we're going to put the drop timer. Now, we're going to have a drop timer length. Let's define what that's going to be. And this is in frames. So we'll make the drop timer length. To start off with, let's just have it drop 1. Is that 50 or 60? That's 50. For the moment, let's start with having the timer fire once a second. So the piece is going to drop once every second as it goes down. Okay, so here's what we'll do then. So we need to actually set the value in the drop timer. So we'll do that as part of the setup here. Load drop timer length. Spell right. Spell things correctly. All right. And store that in drop timer. Now in the game loop, here's what we'll do. Every frame we're going to decrement drop timer. If it doesn't equal 0, we do nothing. We're just going to hop over this. We're going to drop timer not expired. It'll be nice explicit labeling here. Drop timer not expired. So then right here is where we're going to put in the code to actually drop the piece. However we do that. And then we need to reset the timer. So let's do that before we forget. So reset the timer and then drop the piece. Now, let's just make sure this timer's working. So we're going to do the old change the background color trick. So I'm going to increment the background color, and just in case you've forgotten, I'm doing it twice because in most graphics modes, including this one, the least significant bit of the color code doesn't mean anything. It's just completely ignored. So if you want the color to actually change, you need to increment twice. So we'll do that. All right, so we'll go ahead and kill the emulator. Rebuild the program and run. If this worked correctly, every second we should see the background color change. Oh, there it goes. See, it's just becoming more and more gray. It'll become a new color eventually. White. There. Yep. Now it's going. It's in the next color now. We're going through those brightnesses. Kind of a greenish yellow kind of deal. Okay, so the timer works. So there's our 1 second timer. And let me find the mouse cursor so I can kill this. Okay, so having done that, we now have a functioning timer. So now we just need to figure out how we're going to drop this piece. All right, so there are 2 parts involved in making this piece drop. The first is to update the stored values to reflect the new piece position. The second is to update the graphical component of it. So we need to blank the previous locations and write the new ones. Now, you could get super fancy with this and only change the things that need to be changed, right? Because let's look at a piece here. We're not going to get super fancy with this because it's too hard. But for example here, with this piece like here, the very bottom space there, if we were to drop it straight down, that actually wouldn't change because the one above it's coming down, into it. So if you wanted to get super fancy, you could do this in a way that you didn't move every single block because some of them won't change. But honestly, it would probably take more work and more ROM space and more processor cycles to figure out which ones you should move instead of just moving them all. And there's only 4. It's not a big deal. So we're just going to move all 4 of them. I'm going to leave this open as a reference. I don't personally need it, but maybe someone does. So I've written Tetris so many times by now. Okay, so here's what we're going to do then. All right, so I said there are 2 aspects to this. We have to update our stored values so we know where the piece is at now. And then we need to update the graphical values. So here's how I'm going to do this. I'm going to do this a simple brute force way. So the first thing we're going to do is erase the old piece. So how do we do that? Well, here's what we're going to do. We have 4 values to erase. So we're going to, now these registers are all going to get clobbered. So we're going to start index 3, and we're going to put this somewhere safe where we can reload it. So put in F0, which I'm pretty sure is safe. And then we'll start the erase loop. All right, so here's what the erase loop is going to look like. We're going to, okay, so we need to prepare data for this lookup function that gets us to the memory cell to address. So we want the x coordinate in x and the y coordinate in y. So every time through the loop, wherever I lost it, where is it? Game, there we go. So every time through the erase loop, here's what we're going to do. We're going to load y with our current index. Then we're going to load, I don't think I can load x directly, but let's try it anyway. We're going to load x with current piece x indexed by y. I don't think I'm allowed to do that, but let's see. No, I can't. I have to kill this before I can rebuild. Oh, I am allowed to do that. I didn't know that. Okay. We'll reopen the emulator. Different piece, though. Oh, okay. I didn't think I could load straight into x that way. All right. Hey, you never know. All right, and then we're going to load into a current piece y, indexed by y. So now we have the current locations. Got them both here. And now that we have that, we're going to jump to that function that converts those to the cell location, which is cell to address. Now, this is going to clobber all my registers, so this is going to be a little bit messy, but there's really no way around it. So we could jump to cell to address. Now, cell to address puts the address of the memory cell for the board that corresponds to those x and y coordinates into FEFF. So now we need to write a 0 there to erase it. We're going to load 0. We're going to also put the 0 into y because you have to index when you dereference 0 page. You need an index. And in this case, the index is 0. And then we're going to store that 0 to that indexed address. So this will blank the spot where that was. Then we're going to decrement F0. And if it's not negative yet, we branch on plus back to erase loop. Okay, so if I did this right, that should erase the current piece. So let's see if that works. You gotta test these things one piece at a time. So if this is correct, the screen's gonna come up, the piece will be there for 1 second, and then it'll just disappear. So let's find out. Piece, gone. Excellent. Okay, so we can now erase the piece. So that was step 1. We've erased the piece's old location. So the next thing we need to do is to change the actually, you know what? No, you can't do an indexed increment, but we don't need to. Okay, this is going to be a little easier than I thought. So when a piece drops, all we're really doing is incrementing all of its y coordinates. The x coordinates aren't going to change. So the update to the old values is extremely easy. Increment. Actually, let's do this in a loop because we need to go through all of them anyway. So here's what, no, because you can't increment with an index. So we're going to do increment. This I don't think you can. I'm pretty sure you can't. But you know what? I didn't think you could load straight into X either. So let's try. I don't think this works. Correct. That does not work. Okay. So we need to increment all of the values. So here's what I'm going to do. I'm just going to increment them all. It might be possible to kind of work this into the next loop we're going to do, but it's going to require a bunch of register juggling that I would prefer to not do. So we're just going to just do it. So a higher numbered y coordinate is closer to the bottom of the screen. So by incrementing all those y's, we've just moved the whole thing down one thing. So now we need to draw it in its new location. Now, we could probably rewrite the generate new piece code in a way that allows us to kind of reuse a bit of this. So what the generate piece code could do is it could just fill out that current piece location data and then call another subroutine that says draw wherever the piece is. And then we could reuse that subroutine here and just say draw wherever the piece is. In fact, in the long term, that is definitely the better way to go because we're going to be moving the piece in a variety of different ways, right? Not just dropping it. We're going to be moving it left, we're going to be moving it right, we're going to be rotating it, all kinds of stuff. Although I think for the moment, like just for now, to get it working, we're going to just stick it right here. But I think in the long term, we're going to want to take this code, pull it out, and put it into a subroutine. Wait, you know what? No, we'll do it right now because it's not that hard. Here's what I'm going to do. I'm going to JSR to draw current piece. So let's go right draw current piece. Where are we going to put it? Put it right after generate new piece. Okay, so what this allows us to do is now any change to the piece's state is just a matter of updating those 8 bytes on 0 page that identify where the piece is right now. So all you need to do is update those numbers and then call this and bam, we draw the piece. Now we actually might want a corresponding piece erasure function, but we'll get to that. Okay, so how do we draw the current piece? Well, we're going to do a very similar thing. We're going to start by putting the number 3 somewhere safe because that's our index. Then we'll do a loop. So here's what we're going to do. Load y, load the index, load, okay, so that's right, because we can go straight to x. So x is the x position. Load current piece x, piece x, y. So there's the x coordinate. Load a, current piece y, y. There's the y coordinate. Then we jump to cell to address. That'll resolve the address. And right now we're using the number 2 for the pieces. So we're going to put the number, that's cell number, tile number 2. Oh, wait, I got to load y number 0. And then we write that to that location. And then again, we decrement F0. If it isn't negative yet, go back and loop, return from subroutine. Okay. Well, let's see if this works. If this worked, our piece should now just start dropping down the board. The problem right now is that we have no border control. So it would just go right through the bottom. But we'll get to that. So here we go. There it goes. Look at it go. 1 second at a time. And like I said, it's going to plow right through the bottom and probably wrap back around to the top. Actually, I don't know what it's going to do. It's definitely going to go through the bottom. I don't know what it's going to do once it goes off the bottom. Probably just start wandering through random memory. Wait a minute. Oh, I know what happened. The lookup function doesn't consider rows beyond the dimensions of the board, so it's probably just writing into some crazy memory location right now, and will probably eventually hit something critical and crash the system. But hey, it's the price you pay, you know. But we got the piece to drop, so that's good. Piece did drop. So what do we have next? So there are a couple of problems with this. One is, first of all, the piece does not stop. It just keeps right on going. That's problem number one. So how then do we deal with that? Well, there's a couple of different ways. So we want the piece to stop when it tries to move and there's something below it. So we need to be able to identify that there is something underneath the piece. And that's actually pretty easy. You just look at the tile ID at that location. Because we have tile 0 is an empty tile. So we need to know if there's an empty space there or there's something already there. Now, there is a slight complication to this, though, and I have a technique that's going to help us with it. But we'll get to that. We need it right now, actually. So the way to do this is to, before you move the piece down, you need to check all 4 pieces to see if the space underneath that block is clear. Oh, wait, no, we don't. Well, no, because we wouldn't want to erase. Never mind, we do need to do this. Okay. So before we do anything with the piece, we want to check to make sure if the space underneath each of the 4 blocks is clear, because that's the general answer, right? Like the worst case scenario is that long piece laying on its side where all 4 blocks have to hit something. So you might as well just do the general case, even if you could get smart about this. The problem, though, is that, take this example here, the topmost block here, there's always something underneath it. So you need to be able to distinguish between blocks that are at rest, that are already in the playfield, versus the ones that are actually the components of the currently dropping block. And there's a very, very easy way we can do this. What we're going to do is we're going to take this tile. This is the piece tile right here. So this is 0, the blank tile. This is 1, which is the background tile. This is 2, which is the current piece, little square tile. We're going to make a copy of this. This is going to be tile number 3. And now we're going to look for everywhere where we were writing tile number 2. So I'm just searching for, let's search for number 2. Here we go. Okay, so here, that has nothing to do with it. Build screen. Okay, here we go. All right, so I think actually before we go any further, we should probably factor out the draw current piece. So, no, we'll leave it for now. So what we're going to do is we're going to use tile 3 instead of 2. Okay, I'm going to switch it to tile 3, and I'll show you why I'm going to do that in a moment. Okay, so it looks the same because those 2 tiles are identical. So what we're going to do is we're going to use tile 3 for the pieces that are part of the active piece. The tiles are part of the active piece. And tile 2 is going to be the pieces that are already in the pit, the ones that are at rest. So when this block stops, when we actually have code to do that, we're going to convert all those 3s into 2s. So now we can tell the difference We can tell the difference between squares that are filled with pieces that were there previously and squares that are part of the current piece. So now the test for can this block fall is if the tile underneath is 0, yes, it can fall. If the tile underneath is 3, yes, it can fall. In fact, you know what? We're going to do this even better. There's an even smarter way to do this. I'm going to do a little bit of juggling here. We're going to take this and we're going to put it up here. We're going to make it tile number 1. Okay. This is now tile number 1. So we need to change the that background tile is now tile number 2. So let's go up here to draw a current piece. We're going to draw a 1. And we're going to do it with the 1 here too. All right, so when we build the stage, the background here, we were using 1. Now we're going to use 2. Okay. So I've rearranged the tiles, and let's just make sure this still looks like it the way it's supposed to look. Whoops, what did I just do? I have no idea. Oh, I had an error. All right. Then I got a stray dot. There we go. I can't even see that. Oh, my poor eyes. I should be getting cataract surgery next month. Or at least starting the process next month. I'm very excited about that. Okay, so now... There we go. Looks the same. So for some reason it appeared on my second monitor. Why did you do that? Okay. So now what we've done is we've changed the tile IDs. And I'll show you why I did that. Because what we're going to do is we're going to use tile 1... This is tile 1, as the squares that make up the currently falling piece. And we're going to use tile 3 as the squares that are currently in the pit. And the reason we're going to do this is because now the test to see if the square underneath the square is empty is very simple. We compare to 1. If it's greater than 1, it's not empty. So by putting the two valid cases together, we simplify the test. Because before it would have had to be is it 0? Okay. Is it 3 or whatever I meant? Okay, we'd have 2 values to test. Now all we do is compare against 2 or 1 or 2. It depends on how we do the logic. But we would just look for, is the tile greater than 1? If the tile is greater than 1, then that space is full. And we're not going to drop down there. Okay, so let's see what we can do here then. Where are we at? Okay, here we go. Game loop. So, all right, so if the drop timer expires, we reset the drop timer. Now, right now, we unconditionally drop the piece. We don't want to do that. We need to check first. We need to say, can this piece even fall? So, how do we do that? Well, we have to go through every single piece and check what is underneath it. What are the coordinates? What is in the square underneath the piece? If the answer to all of that is 0 or 1, then the piece can drop. No problem. So, how do we do that? Well, after resetting the timer, we're going to do this. We're going to do pretty much the same thing here. We're going to load 3, store it to F0, and we're going to call this the drop check loop. So here's what we're going to do. We'll get index 3. We'll get current piece XX. Yeah, expect this sort of loop to come up a lot. Because every time we do anything with this piece, we're pretty much going to need to do the same loop. And then we load A, current piece. Whoop. Now we're going to load current piece Y. Okay? But the cell we want to examine is the cell that's one space down. So we're going to clear the carry bit and add 1 to the accumulator. So this gets us 1 step down. So this is the space we want to look at. And then we're going to jump to subroutine, which is cell to address. So now address FEFF has the cell that is one space below where this block is. So now we're going to load that value. Compare it to 2. Branch on carry set. So if it's 2 or higher, I think branch on plus would actually work here, but we're going to use branch on carry set. If it's 2 or higher, this is not a valid move. Something is there to obstruct this piece. So in that case, we need to branch to somewhere. I'm going to rename this label. I'm going to call it drop done, because now we have 2 reasons to go there. Only one has to do with the timer expired. So we're going to branch on carry set to drop done. As soon as one of these checks fails, that's it. We don't need to look at any others. We're done. If drop is not done, we continue the loop. So we deck $F0, branch on plus to drop check loop. Okay, now I think this is going to work. Ooh, actually there's one problem with this. And that is that when we get to the bottom row, it's going to try to look down, but there's no entry for that in the table I made that figures out the addresses. So we need to add an additional entry to this table. We need to have a theoretical 21st row so that the collision checks will hit that. So we're going to go fix that. So this is my table here. So we need to add one more entry. It's going to be... I gotta get my calculator because I'm no good at hex math. If I'm reading this calculator right, 7F. Okay, so the next address is 7F, and it's still going to be 23. Okay. All right, so I think that might work. So we have to watch it fall. I think now it should stop at the bottom. Let's find out. Here we go. It's going, it's going, it's going. Is it going to stop at the bottom? The tension is it's just so much here. I'm worried. I'm afraid. My programming skills are being judged. Look at that. It stopped. There it goes. So now this idea, I want to talk a little bit more about this idea of having sort of these theoretical rows that exist outside the boundaries of the board. Now, I've done this several times with the various Tetris clones I've written, where you do have extra logical rows that exist outside the boundaries of the box, and they can be very useful. But I didn't want to do those right away, because I wanted to, kind of demonstrate why you would do that rather than just doing it right off the bat and saying, oh, it's something we'll need. Don't worry about it. No. So you see now why you might want to do that. Now, the side ones are less of an issue because we can very easily get to the side ones by just decrementing or incrementing the X address. But, we'll look at it. They might change. We'll deal with these problems as they arise. But for now, we have a piece that stops when it hits the bottom. How cool is that? Now, that's neat and all. Let's watch another one. Oh, it's a square. So watch the square drop. Go square. Go square. Go square. Square. Okay. Well, that's pretty cool, huh? So we made the piece fall. We made the piece land. So I think the next thing we need to do then is to change a little bit of what we did here. So what I put in here is if the test failed, we immediately just said, okay, we're done. But that's not what we need to do. What we need to do when the fault test fails, we need to jump to some code that's going to insert the piece into the board. So basically, we're going to take those tile 1s that they were and convert them to tile 3s, which are now fixed pieces in the board. And then we need to call the routine to start a new piece dropping. So, how do we do that? Well, we BCS to drop done. That's not where we want to go. Where we actually want to go is... I don't know. Where do we want to go? We'll branch to ground piece. So I'm going to put ground piece right here. And I'm going to, right here, we're going to have to jump to drop done to get over it. Okay. So this is ground piece. This is where we're going to take the piece and ground it. Excuse me. So we're going to have to do our loop again. Like I say, get used to this. It's going to happen a lot. We'll call this ground loop. So here's what we're going to do. Load Y, load F0, load A, current piece X. Actually, that goes into X. Current piece X, Y, load A, current piece Y, Y, and then JSR to cell to address. Only 2 Ds in address. That's very important. Remember that. Most important Atari programming fact. Only 2 Ds in address. 2 S's as well. Don't make that mistake either. All right, so now that we have the address, this is the address of one of the blocks in the piece that's just been grounded. So we need to take that block and change it to a tile ID 3. Great. Then we deck F0. If it's positive, continue looping. So at the end of this loop, we have just changed that piece from a falling piece to a fixed piece. It is now in the board, and the collision detection will see it there and say, oh, there's a piece here. But after we finish the loop, we need to start a new piece. And I don't remember what this is called. Generate new piece. So once we have finished grounding the old piece, we're going to call generate new piece. And then we'll continue. So let's see what happens here. This should cause a bunch of pieces to start stacking up. So let's see what happens. Here we go. Here comes a little, I think I call this an S piece. There it goes. Falling. Falling. It's beautiful, isn't it? And... oh, here comes a new piece. Look at that. We got a new piece coming. Here it comes. And it should nestle nice and snugly right into there. Yep, like a glove. Oh, here comes the L piece. Now, at the moment, of course, we have not done anything regarding the top of the pit. So eventually it's going to get to the point where it's just going to keep spawning new pieces and they're all just going to freeze to the top because they have nowhere to go. Oh, there we go. This is going to fill a lot of space. Isn't it cool to do stuff like this and to watch it? It's like, man, I did that. I mean, I did that, but you could do this. Just do what I'm doing. Oh, here comes another one. We got to change up these colors. I need some better colors in here. Oh, and the L. We're almost full. Almost. I just want you to see what I'm talking about at the top here. Yeah, so this is going to get real stupid now because these pieces, okay, that one fits, but now they have nowhere to go, so it's just going to keep spawning pieces over and over again, and that's just what it's going to do. But the important thing to note here is that we have actual collision detection. So the piece falls, it lands, and we convert it into a fixed piece that is actually in the board. So that's pretty good. And some good stuff. So, man, this is good progress already. I mean, I'm doing this for just about an hour so far, and we've already got pieces falling. We got collision detection. We got new pieces appearing. This is good stuff. We're good. We're doing good. This is something that really does fascinate me about, just the system and the assembly and all that. Is that once you learn what you're doing, you have to write surprisingly little code to make things happen. I mean, look what we did, right? This right here just kicked off that whole tower of pieces, right? And that's not that much code. It's like 9 or 10 lines of code. It's not that bad. You just got to learn the tricks. I love assembly programming. It's just so much fun. So moving on, what can we do next? Well, I suppose left and right movement might be something we want to try. Now, this is going to be kind of interesting, and again, this goes back to some of my ulterior motives for doing this game, because I want to do a game like this, and I have a lot of unanswered questions about how I'm going to do certain things. So I'm trying to figure a lot of this out for myself while I'm doing this. Control is going to be a major issue because the 5200, of course, has the analog joysticks, and analog joysticks seem like they're not going to be very good for this kind of game. Now, on an emulator here, I'm just using the keyboard, so we have digital control. I may take this at some point, throw it on my SD card and my Atari Max card and try it on real hardware with a real joystick and see how it feels. I feel like it's going to be terrible, and I might need to tweak it. But if we're going to do control, we're going to start by doing very simple control based on the fact that at the moment it's actually digital. If you were to take the code I'm about to write and put it onto a real 5200 with analog joysticks, it might be terrible. I don't know. We're just going to have to find out. But if it ends up being real bad, like if I test this next week and say, geez, that was awful, I need to fix that control code, I might do that next week during the week. And if I'm hoping to do another one of these on Friday, maybe. If I do another one of these next Friday, if I have fixed the controller code to be better, I will show what has been done and how I adapted that to the analog controller. But let's see here. So before we get into moving the piece left and right, I think the first thing we want to do here is do a little bit of code cleanup and refactoring. Now, in particular, this whole erase section, I want to put this into a common subroutine. So we're going to take this and factor it out. So going here to where we have draw piece. We have draw piece here somewhere, right? Generate new piece, draw current piece. All right. Right next to it. Actually, you know what? I don't even need to copy the code. I just need to copy this code and change what I write because it's the same thing. I'm going to take this code. Call it erase current piece. Now, it just occurred to me, if you really wanted to get fancy with this, you could actually use the same code for both of these and just have a location where the calling code places the value to be written for the pieces. In fact, let's do that. Let's do that. I like that idea. Here we go. We're going to change the name of this. We're going to change this to update current piece. And what it's going to do is it's going to fill in the current piece with the value at address F1. Okay, so now here's where we do draw current piece. So before the loop, erase loop. What is the erase loop? Oh, here we go. All right, here we go. Before the loop, we're going to put 1 in F1. Now the erase loop is not going to be a loop anymore. I'll get rid of this. So the erase loop is just going to be put 0 in F1. Actually, you know what? We'll just pass it in the accumulator is what we'll do. So whatever value's in the accumulator, that's what's going to be written. So load 0 and then JSR to update current piece. And the very first thing update current piece is going to do is save that value that came in the accumulator to F1. Okay, so this allows us to unify the drawing code into a single routine. Okay. Now, just as a point of interest, it would be slightly faster to make them two different routines, because loading a literal number is one cycle faster than loading from a 0-page address. So we're trading performance for convenience and code size here. But if if code size wasn't an issue, which it probably isn't for a Tetris game, honestly, it would actually be faster to write two functions that use their own literals. But we're not going to do that here because this is Tetris and it's not that complicated. We don't need to worry about that saving cycles. That is surprisingly a general rule. A lot of people don't realize that about assembly languages. Quite often, larger code is faster code. And that's something that a lot of people don't realize. I, as part of my degree, I did a lot of studying on compilers and optimization, stuff like that, and how they do their job. And you learn the various tricks that compilers use to optimize code, and you realize that quite often, bigger code often runs faster for various reasons. So there tends to be, which is why for compilers for a lot of higher level languages, you see among the optimization options, you often have optimized for performance versus optimized for speed, or optimized for size. And those two often go at odds with each other. Not always. I mean, there are definitely cases where smaller code is faster. But I think the overall trend is actually that faster code does tend to be larger. Because you get into things like loop unrolling and function inlining and stuff like that. But that's a theoretical discussion. That's not relevant to this. So we now have isolated that. So let's go ahead also and go here to generate piece. So generate piece now is not going to write to we're not going to do cell to address. We're just going to update the current piece. Again, this is going to be slightly less efficient. You know what? No, I'm going to leave this I'm going to leave this alone because we're going to need to revisit this in the future. If we decide to add the next piece box, we're going to need to revisit this. So I think I'm going to leave this as it is for now. Because if we come back to do a next piece box, this is going to need to change anyway. Because the new pieces generator doesn't go straight into the board. It goes into the next box. And before that, the piece that was in the next box needs to be transferred into the board. So it's actually a two-step process. So we'll deal with this later. All right, anywho. So we want to talk about moving left and right. So here's what we'll do. Well, first we check the drop timer. Great. Now, if the piece has been grounded, I think at that point we don't. Okay, I'm going to put the input code after the piece grounding code, but I don't want the input code to. I think if the piece has been grounded, we want to end the loop right there. Well, actually, if the piece has been grounded, we then need to jump to the line check algorithm, which would come next. If I always put a note in here on that. Put a to-do line check. But for the moment, I'm going to have it jump right back to game loop. So down here in drop done, this is where we're going to put the... excuse me. This is where we're going to put the input code. All right, so now here at the moment, we're just going to do left and right. So there are 4 inputs in Tetris, 5 if you want to get fancy. So the 4 inputs are move left, move right, drop fast, rotate, and if you want to play fancy, you have 2 rotates that go different directions. So there's a minimum of 4 inputs, 5 if you want to get cool. And of course, pause and all that fun stuff. So what we're going to do is we're just going to check for the left and right input. And we're just going to use stick once. That's going to be... So we're going to load the pot 0 shadow. So this is the horizontal axis on controller 1. So now we need to decide what our dead zone is. Here's where it's going to get awful, this analog joystick. So as I mentioned in the earlier videos, I tend to use value 110 as my approximate center on the axis. So we're going to compare against a certain value like plus or minus off of 110. Let's go with 70. So 40 then. So we're going to compare it to 70. If it's less than 70, we're going to go to move left. Compare to, okay, so that's 40 less than that. So compare to 150. If it's greater than that, we'll go to move right. Otherwise, we'll jump back up to game loop. And here's where we're going to put move left. And can't type. Move right. Okay. So, move right. Yeah, my eyes. I just can't see this stuff. Okay, so. All right, so now we have code that should pick up on the joystick and do that. But you know what I'm going to do? We're going to test this. As always, we're going to test it. So if we're moving left, we're going to decrement the background color. And if we're moving right, we're going to increment it. Now, I'm only doing it once here because this is going to trigger every single frame. So I don't really need to double up on it, but here we go. Right, and it gets brighter, and left, and it goes the opposite direction, it gets darker. Okay, so we got our input. Fantastic. All right, so we're reading the joystick. That was easy, right? Of course, I'm doing that because I've already done all the setup. There's actually a lot of setup of the various system registers involved with reading the joysticks. I covered all that in a much, much earlier video, so we're not going through that mess again. All right, so we've got the left and the right. Now, how do we do something with them? So, here's where we're probably going to want to do our own little check again. So, we could now... All right, so something we could do here, which would probably be useful, we might want to do it now, is to come up with a common piece validation code, because there are going to be a lot of situations where we need to take a potential piece position and evaluate it and say, is this legal? So right now we have this check for falling, where we check one space down. But we're also going to need, can you move left? Can you move right? Can you rotate? So what we want to do is to have a common piece of code that we can call with this potential piece location, and it'll do all this work, and it'll return good or not good. But this means we need somewhere to stick 8 inputs to this function, because we have 8 coordinates that we need to do. Now, for movement, there is a way we could simplify this. We could actually pass 2 pieces of information, being an X delta and a Y delta. And I could apply the X and the Y delta to the existing position and use that. That would work for movement. That's certainly something that could be done. But it does not work for rotation at all. I mean, that's not even close. So if we want to do a generalized movement check routine, we need to have somewhere where we're going to put this data, the values that we want to check. I mean, now, there's not enough registers to do that. And I really don't want to suck up half of my, a big chunk of page 0 locations that passes Although, well, we might have to. Okay. So here's what we're going to do, actually. We're going to have a dedicated page 0 window that holds the potential piece location. And when we want to check if a piece move is legal, we're going to fill those 8 bytes in with the place we want the piece to go to, or the state we want it to occupy in the case of rotation. And then we'll call this routine that will use those values to check to make sure that everything's cool to do that. So here's what we'll do. We'll put it fairly high up on page 0. Now I use F0 through FF for just like local scratch variables. So I want to stay away from that. But I'm going to put it then, we're going to put it at, we'll call it test piece X. And I'm going to put it at E0. And then we'll have test piece Y, which will go at E4. So this little range here, we're going to reserve that for this one specific case because we're going to need it all over the place. Might as well do it. Because we got plenty of page 0 memory. You don't need a lot of memory for Tetris. So this is where we're going to put our test values for whenever we want to check a piece. So let's go ahead and take, we're going to, okay, so here, where did we do the drop OK thing? There's a drop? Here's the drop check loop. Okay. So we're going to take this drop check loop and we're going to move it into a more generalized piece of code. All right. So we'll call it validate. What did I call these variables again? Test. That's not very good. Validate P. Let's call it validate piece. Okay, so this is going to do what this does. It's going to take all of... take this. Let's put a comment here. Okay, so this is the code I just stole. I wrote it. Didn't steal it. All right. So here's what we do here. So we can use simpler labels now because we're in our own subroutine, which is always an advantage. All right. So we do this. We're going to load from current piece. We're going to load from test piece. And this addition can go away because this is what adjusts it down. So we're looking one step down. We just go straight to cell to address, load it, check it. Now, instead of branch on carry set to ground piece, we're going to branch on carry set to invalid. Actually, no, we're going to branch on carry set to done. I'll show you why. Branch on plus to there. Clear the carry bit. Done. Return. So we're going to use the carry bit to communicate the results of this. And that just happened to be convenient because of that one branch instruction. So when you call this, it's going to check to see if the test location is valid. And if it is, it's going to set the carry bit. No, excuse me. It's the other way around. If the carry bit is set when this function comes back, then the move is not valid. So we're going to use the fact that we branched on carry to communicate the result of the function, which is why I cleared the carry bit here to make sure it's clear. So, although you know what, it might be clear. DAC doesn't touch the carry bit, I don't think. So I don't think we even need this. I think it's going to be correct anyway. Well, we'll find out. I think the carry bit's going to be in the correct state either way. So we're going to use this validate piece. So this means, though, that before we call validate piece, we need to set up that test region. So here's what we're going to do. We're going to load Y, number 3. There's our index. We'll call it drop test loop. We're going to load A, with current piece X, Y. Now, X doesn't change when we're dropping. We're only interested in Y. So we'll load current piece X, Y. Store that baby to test X, Y. And we're going to load X with current piece Y, Y. Now we're going to increment X, because that moves us down one row. And store X to test Y, Y. It's test piece X, I think. Then decrement Y, and as long as it's positive, we continue the drop test. And then we JSR to validate piece. And then if carry is set, ground the piece, because carry set means no, this is not valid. You can't go that way. So now if this works, let's go ahead and test it out. Unresolved symbol, drop check loop. Where do I have drop check loop? Where do I have drop check loop? Whoa, okay. I forgot to shorten that. It's just loop now. Okay, so if I did this right, we should see exactly what we had before, but now we have a nice generalized function for doing it. So here we go, we're dropping. I think after 2 pieces drop, I think that'll be sufficient proof that the new method works. But yeah, having a generalized piece check is very important. It's very useful. And when we get to rotations, we're probably going to have a rotation table for each piece. So we'll just be able to pull the values out of the table, stick them into those test locations, call the function, and go. Tables are definitely the way to go for rotation. I believe it's working. Okay, so. All right. So we now have a generalized piece update, which can erase or draw pieces however we please. We have a generalized piece validator. So with those 2 powers combined, we should be able to do left and right movement. Now again, truly fancy, you would maybe find a way to combine the piece dropping with the left and right movement, because we would be kind of possibly moving the piece twice. But if this were a much more complicated game, that might be a performance issue. It might cause issues, but not here. And that's one of the things that, especially working on a system like this, you need to get used to, especially if you're coming from a more conventional, like a PC programming background, where you really got to think about, in a system like this, if you have the time to burn, then burn it. Like, it doesn't matter. And similar for things like ROM usage, right? I mean, this is a 32 kilobyte ROM. You can waste space gratuitously as long as you can fit everything in, just do things in stupid ways. As long as everything fits, doesn't matter, because it's a 32 kilobyte ROM no matter what. And some of my published games, I've definitely done that. Like, I don't care. It's 32K. I've only used 24 of it. I got 8K left to just do whatever I want with it. Okay, so here we go then. So how do we move left then? Well, very simply, we need to set up a test, and the test is going to be to decrement X all the way. Now, here's where we need to be a little bit smarter about how we do this. Okay, I think I'm going to do this the simple way. All right, so we need to load our loop index, which is 3. So here's what we're going to do. What did I call that previous loop? Drop test loop. Okay. I like to try to be consistent with my label names. Can't always do it, though. We'll call this left test loop. Okay, so here's how we're going to do this. I'm going to load... Actually, I'm going to load into X. Load X with current piece X, Y. Now, if this piece is against the far left side of the pit, we can't move. And we want to catch it because right now, if I were to, what I would want to do to move left is to decrement every x coordinate. But the problem with that is that that's going to screw up all the code for the, what I'm trying to say, for all the board checks, because that'll make x -1 or 255, depending on how you interpret it. And it's going to get really screwy real quick. Now, you can mitigate this by making the board logically larger than it appears and changing all your coordinates, to affect it. I think I'm not going to do that. Or, no, you know what? Let's do that because it's going to be simpler than I think. So here's how we're going to do that. So we're going to add an extra column on the left side. And that's going to be column 0. So in order to do that, I think it's actually going to be relatively simple. So these are all the row addresses here. So I think I just need to, I just need to decrease each row address by 1. That's the first step. So here we go. So E6 E. Okay, and that didn't affect any of the high bytes. And then these coordinates here now have to be updated. So I need to increase all of these x coordinates by 1 because x coordinate 0 is now off the left edge. Hopefully I got all those right. Okay, so if I did that correct, things should still look the way they did previously. And it looks like they do. Okay, so now in effect what we have is we have an extra column on the left side. So now we can test against that column because it's not going to be negative and like get some crazy overflow value or something like that. So having made that change, now up here where we're going to check left movement, here's how we're going to do that. So we're going to take current piece X, decrement it, because we want to move left 1, and write it to test piece X, Y. Then we'll take current piece Y and write it to test piece Y, Y. Then decrement Y, branch on plus to left test loop. Okay, so now we've set up the data. Now we jump to validate piece. So, if carry is set coming back from this, then it is not a valid move. So we'll BCS then to move done, which will be down here somewhere. But if carry came back clear, this is a valid move. So now we need to actually move that piece to the left. So here's what we'll do. We'll just deck. We'll do pretty much the same thing we did up for the Y thing. Yeah, actually, I forgot to erase the old piece. Okay, so we need to erase the old piece. So we'll load A, 0, update. I think I call it update current piece. And then after changing all these values, we load number 1 and update current piece. Now there is one more element we're going to need here, but we'll come back to that. So, whoa, okay, so I messed up. Okay, that looks like the... Which piece is that? That must be the straight piece. I screwed up the conversions here. Let me go check that. I was afraid I might have missed up one of them. Yeah, these should all be 5s. I messed one up. All right, fix that. Okay. So now, if I push left... No, okay, I screwed up another one, but... Whoa. Okay, everything's going crazy here. All right, so clearly things are not happy. So first of all, it looks like I screwed up this table a little bit. So let's get this table corrected. All right, T piece looks fine. All right, so I think what I'm going to do is I'm going to force each of these pieces so I can look at them and figure out which ones I screwed up. So instead of random here, we're just going to load 0 and test each piece in turn. It shouldn't take too long. All right, so L piece looks fine. Reverse L looks fine. That's not right. Did I? That should not... Well, what is going on here? Two should be the S piece. Why is it giving me the L? There it goes. I wonder what's up with that. Anyway, that one looks fine. All right, Z piece looks cool. T piece looks fine. That one does not. What is that? Oh, that's a square. 5060. That should be 51. All right, there's our square. And finally, the straight piece, which I'm pretty sure we know works, but let's go ahead and double check that. Can't be too careful with this stuff, you know. There we go. There we go. Okay, so we fixed that up. Now, the moving left, though, is way out of whack. So let's see what's going on with that. Whoa. Okay, so moving left is very much not functioning correctly. Let's go back and analyze what's going on here. Debugging. It's the most fun part of this stuff. But very important. Debugging these types of systems is actually very difficult. I mean, emulators do typically have very nice debuggers that you can use, you know, to work through a lot of these problems. But you need to get creative sometimes. Okay, so let's look at move left. So what happens here? We load 3 into Y. We load the current X location, indexed by Y, decrement it because we want to move to the left, so we go down by 1. Store it to piece X, test piece X, come Y. Okay, we load the Y coordinate. We don't want to change the Y coordinate, so we store that to test piece Y. Oh. No, never mind, never mind. Why did I day? Oh, I dayed because it's a loop. All right, so we decrement Y, branch on plus to the loop, repeat the process. Okay, so that should put the location we're interested in into the test piece area. Then we go to validate piece. Now, I'm going to assume validate piece is working. Let's carry on. If carry is set, then we can't move. We shouldn't move. So move done. And we jump back to game loop. Otherwise, what do we do here? Load 0, update current piece. That should erase the piece. Then we decrement. Oh, geez. I see what I did. It's supposed to be 1, 2, 3. I was decrementing the main X piece 4 times. All right, so let's see if that works. Look at that. There it goes. We moved to the left, right into the wall. It's not going any further. Now, the one thing I mentioned just a moment ago, we're still missing something here, and that is that we really want to have some kind of a move timer. Because when that thing moves, it's just going to go. It's going to zip over 1 space per frame, and that's way too fast. So we need some kind of a move timer to pace this move. But we need that to move right as well. And probably for rotate. We might want a separate timer for that. No, rotate could just happen on button press. So before we screw around with this timer that we definitely need, let's go ahead and do the code for moving right. Because it's going to be pretty much the same thing. But we need to have, again, that sort of virtual right column. But you know what? We already have it. It's already there. We had to do something special for left because we would have underflowed the index and gone down to -1 or 255 or whatever. And none of the math would have worked at that point. But going right, the math still works. Because what is now, 10 wide? What is now column 10, which is the rightmost visible, like active column. Column 11 is just the next byte over, which is part of the background. So we shouldn't need to mess with any of that. So those extra right columns, those kind of already exist at this point. So we don't need to worry about that. So all we need to do for move right is pretty much the same thing we did for move left, except we're going to increment X instead of decrementing it. So we're going to take this same code here. And again, just as an interesting performance thing, we could factor this out. We could factor this out and do something delta-based where we just say, I want to move -1 and apply that to X. And that might be more convenient, but it would be slower. Because again, quite often larger code is faster. The more explicit operations are faster, but whatever. Actually, it would be more difficult. It would be much slower actually to do that because here we know we need to decrement. In that type of scenario, we would have to, we know we were decrementing. We'd have to actually add it here, and we'd have to add it 4 more times here. So that would actually be a much slower scenario. So we'd have to load the old value, add the new value, write the new value. Or here we can just do dec. Now, dec is a relatively slow instruction, but it's faster than loading something, adding, and then writing it back. All right, so here we're just going to change a few instructions. So dec is going to become increment X, because now we're going right. And here, if we're successful, these are going to become increments instead of decrements. And just like that, we should have a block moving right. Although, I can get rid of that. Actually, I shouldn't be jumping to game loop. I should be jumping to move done because there might be more to follow. So let's just jump to move done. Oh, I need to change the names of the loops too. This is right test loop. Right test loop. Make. Okay, here we go. All right. Can we move right? Look at that. Move right, left, right. How cool is that? And we also get that neat property because the piece isn't grounded until the check for drop fails. So like a lot of Tetris games have, we have that neat property where we can still move here until the drop timer runs out, and then you get frozen. So we kind of get that for free. Now, did I just coincidentally get the same piece twice in a row, or did I screw up the random number thing? Let's find out after this drops. Okay. I thought I put that back. I didn't. Did I screw that up? Or is this just a coincidence in random number terms? Okay, it was just a random number coincidence. 3 pieces, the same piece in a row. Just coincidence. Let's see if we can snuggle that in there. Yeah, look at that. Okay, so that's great. We are so much farther than I thought we were going to get tonight. Okay, so we're up to left and right movement, but we want to slow this movement down. It's way too fast right now. So we're going to want some kind of a movement timer. So the moment we have a drop timer, so let's have a move timer. We'll call this, we'll put it at address 22. I have no idea how long this should be. We're just going to have to try things until we get something that feels good. But I think for the moment, let's go with 15. So it'll be a quarter of a second. Now, the move timer is going to start at 0. So what we do is every time we actually move, we reset the move timer. So down here, yeah, so here's where we actually moved. So we're going to reset the move timer here. And then we're going to move, we'll do it here too. Okay, and then we need to check the move timer. So when we get down here, drop done. Before we even check anything on the joystick, well, we might want to revisit this when we start doing fast drop, but for the moment, we'll do it before we check anything on the joystick. So we're going to load the move timer. Now, if it equals 0, we're fine. Move OK. Put that here. If it doesn't equal 0, we're going to decrement the move timer. And then jump to move done, because we're still in the move timer, so we're not going to move. So I think that'll work. There we go. Look at that. Much, much slower now. That's a lot more reasonable than what we had before. Now, I don't know if that's... I don't know. I think it probably needs to be faster than that, but that's better. Okay, yeah, I think 15 is a little too slow. Let's go down to 10. I think even that's going to be too slow. Yeah, I feel like it's still too slow. I'll try 5. Ah, that's good. I think that's our winner. At least for now. I think that's pretty good. Yeah, I like that. Okay. So, we got our cool move timer. Pieces are dropping. Okay. So, we've almost got a Tetris game here. So, what are we missing? What do we not have? So, we need piece rotation. We need fast drop. We need to check for complete lines and clear them and adjust the board accordingly. We need, what else do we need? We need game over. We need to check when the game is over. We probably want a next piece box. We probably want some kind of scoring system and maybe in a level system. But I'm not sure how much of that I'm going to do. You know, we'll see. But we've made great progress tonight. This is really good. Now rotation is really one of the hardest things, but it's just a matter of building the tables and working with them. It's a little tedious maybe, but you know, it's just something you got to do. But the basic idea for rotation is you keep track of what the piece's rotation state is. And you just have a table of different rotations. And every time you rotate, you move to a different entry in the table and see if that works. Of course, we're also going to need to track what is the piece. Like, what piece do we have so we know what table to use for rotation. So it's going to get a little weird. But we'll deal with that problem, when we get there. All right, so let's see. Times. All right, we got a few more minutes. I'm not sure how much more I want to do today, though. So we got moving pieces. We got dropping pieces. We got new pieces being generated. Oh, something I wanted to check. I want to make sure this works, even though I have no doubt that it does. I wanted to check the left-right movement against pieces already in the pit, because I've been doing it against the walls, but I don't think I've really been doing it like against the other pieces in the pit. So let's see how that goes. Bonk. That's decent movement. I'm definitely going to need to try this out on an analog 5200 joystick sometime next week, and see how that feels. Because, like I said, I'm planning to do a game of this type in the future, and I really want to... Yeah, look at that. Stops right there. Perfect. So we got good collision detection. It's all pretty good. All right, so I think this might be about where I cut off for tonight, because I don't think I want to get too in-depth in anything else. I think the next thing we take on will probably be, well, it's either going to be rotation or fast drop. I'm not sure which one. Fast drop might be the easier one to do, but it depends on how you do it, because different Tetris games do fast drop differently. Some of them, you push fast drop and there's instantly down. Other ones do just a faster fall. I'm not sure which one we're going to do. Just depends on how I feel, I guess. I think that the instant fall is definitely the easier one, or maybe it's not, actually. We could just speed up the drop timer. That might actually be the easiest way to do it. Anyway, there are different options for doing that, and we'll discuss those. But once you do fast drop and rotate, then I think we'll start looking at clearing lines, because at that point it's going to be easier to make lines. So I don't want to do line clearing yet, because it's hard to make lines right now, and it would therefore make it really hard to test them. Now, detecting and clearing lines isn't too terribly hard to do. The hardest part really is probably adjusting the board afterward. But just as a quick description, you actually only have to check the rows that the current piece was on, right? So like this piece here, we'd only need to check 3 rows once this grounded, the 3 rows that the piece was on, and adjust accordingly. So what we would do then is gather all the different Y values and then probably call something that checks all those rows. But that can come later. But look at this. I mean, it looks like a Tetris game. If you didn't know better, you'd think it was working. But that's plenty enough for now. We'll try to do another stream next week. A pre-Christmas stream where we will continue developing this Tetris game. So I will probably on Sunday post this code to the Atari Age forums if you're interested in looking at it and playing around with it. And I guess that'll do it then. So hopefully we'll see you next week, and we'll see how much farther we can push this project.